for symmetric buckling mode, or just called symmetric buckling, it corresponds to the structure like this. Of course, there are many different examples. I will give you the examples I have in mind. For instance, if we have a column and it's connected to a ground. Now this column is also supported by two cables. And the cables actually could be attached to the walls right next to the column. And the loading is applied at here. In this case, when the column buckles, the buckling load, the curve will look like this. We have P, delta, we call it positive delta, we call it negative delta. It looks like this. That's what we call symmetric buckling. And there's another, what we call stable symmetric buckling, and we should call it stable. The next one is unstable symmetric buckling. So what is the case for unstable symmetric buckling? Like this. Exactly the same column, exactly hinge connected to the ground. But this time, somebody came up with a bad idea, a brilliant idea to connect the cables to the ground. So if you do it this way, you do it like this. Loading is still on top. In this case, when it buckles, oops. The curve looks like this, which is unstable. Of course, just to point out that this point is always PCR. Now, how do we know that? It's very simple. If you look at the stable symmetric buckling, when the column buckles, that means the column is going to tilt into one end, and that means the column is going to go maybe something like this. It's going to tilt like this, right? When it buckles. And because the top of the column is connected by cables, and cable takes tension. And that means these two cables would actually provide additional loading capacity against the vertical force P. And that will make the structure more stable. And that's why after the buckling, you still need to provide additional load in order to induce additional deflection. And the deflection here, of course, you already know is the deflection we calculate here. This is delta. So you can imagine that after the buckling, it takes additional force. If we use this to support it. In other words, the cable force will prevent buckling from further progressing. But the other case, as you now see very clearly, one of the cable forces is not preventing buckling, but it's actually helping buckling. And the other one is also helping buckling because the cable force goes downward. The next case, what did I talk about before? Okay, asymmetric buckling. What is the example of asymmetric buckling? Oops. In asymmetric buckling, one example is the buckling of a portal frame like this. Let me try this. Loading is at the top, like this. Suppose we have a frame, and like this. Now, there are two buckling modes for this frame. One of them, you call it mode 1, means when buckling occurs, the frame will deform like that. So I'm going to use this, and that means when buckling occurs, it will go like this. And right here, it still preserves the right angle. Of course, the boundary condition prevents the portal frame at both supports from exhibiting any kind of vertical or horizontal displacements. So there will not be any movements at the supports. In this case, this is what we call the mode 1. And it's unstable. Actually, I'm sorry, mode 1 is stable. In fact, this is going to be one of the examples I will talk about today to show you how we actually calculate this. This is stable. And the other one is this. Right here, you still preserve the right angle. It's what we call mode 2. And mode 2 is unstable. For this kind of structures, the low deflection curve will look like this. Be here. It looks like this. On the right, this is mode 2. On the left is mode 1. In other words, it really depends on what is the direction when the column member or the beam member bends. If it bends toward, if the column members buckles toward the left, it actually would take additional force. And that means it will be mode 1, stable buckling. But if the column member of this portal frame buckles toward the right, it will actually lead to the unstable mode 2 buckling. And let's see other examples, but of course, right now we are still in the conceptual mode. And I hope that once there are 3 other examples I'd like to talk about it today, but we can.
Is it predictable when mode 1 versus mode 2
yes.
can happen?
Yes, that's why you are going to learn from this class. That is going to be your job. One day, somebody is going to ask you, what's your name? What's your name? Falun. So one day, people are going to ask you, Falun, your job is to determine whether this portal frame is going to be stable or not, and what direction of buckling is going to be stable, what is going to be unstable. That will be one of your learning goals in this class, I hope. But let's look at a few other examples more realistically. like buckling of a plate. Again, it's still conceptual because I just want to show you some schematics. Suppose I have a plate and the plate is loaded either vertically like this. And you have loading. In this case, you have uniform loading. For uniform loading, we don't use the force P, we use sigma. So you call this a sigma. Of course, to find the force, you just multiply the sigma by the cross-sectional area, then you get the same force. For this kind of buckling, or it also could be horizontal ones, the buckling curve, realistically speaking, is usually like this. And this is symmetric buckling, so I will not show the other side. I will just show you one side. This is your P, this is delta. For real structures, before buckling, there's always some sideways, which means that in theory, we predict it should be going straightly vertical like this until it arrives the value of PCR. But in reality, what's going to happen is usually like this. There will be some sideways before buckling. And then after the buckling load is arrived for the buckling of a plate in this case, there will be slight increase, almost linearly like this. So this is the buckling curve for a typical, in fact, for a simply supported plate. What about for a column? For a column, something like this, and is subjected to a axial force P, like this. In the buckling curve, looks like this. Right. It will also exhibit some of the curves, but upon reaching the critical load, you will start exhibiting nonlinear behaviors, usually like this, until it fails. That's the buckling behavior of a column. Here I refer to reinforced concrete columns.